And my 5-year-old grandson is in the neighborhood. I can hear him running up and down the hall, so he's liable to interrupt the proceedings. Are you seeing my cover slide?
Yes.
Okay, great. So this is a topic ripped, as they used to say about movies, ripped from the headlines. And it was fun putting together this presentation. Um, let's start with this. This is the particle zoo. This is the standard description of the subatomic world that has existed since the late 60s, early 70s. It involves the introduction by Murray Gell-Mann and others of quarks, pairs of quarks or groups of quarks assembled to produce various heavier particles. It has what are called the leptons, these light electron-like particles, each having an electron charge and the spin, the same spin as the electron. We're going to talk about spin quite a bit tonight. And then there's related leptons that are mysterious particles called neutrinos. We're going to concentrate on the electron and the muon tonight. There's other particles. Since 2012, the Higgs boson has been in the news frequently. So let's start with the history of the magnetic properties of the electron. There was already at the turn of the prior century speculation that there was something in atoms that had angular momentum. This was conceived when people were looking at gradually better and better spectral line resolution of atomic atoms that were in an excited state. So there was the idea that there was angular momentum in atoms, was in the air that early. The electron had just been discovered. And so some people connected the idea that the electron orbiting the nucleus might be the source of angular momentum. And that turned out to be true, but there's more to the story. Niels Bohr, who had already conceived of a very simple model of the hydrogen atom that looks sort of like a mini solar system with quantized energy for the positions of the electron, he had conjured the idea that there was angular momentum not only in the orbit of the electron around the nucleus, but also that the electron itself had some sort of angular momentum, which came to be called spin. But that was in 1913. This is all speculative. He did a computation based on his planetary model of the hydrogen atom, which we now know is the wrong way to describe an atom, but it works. And in fact, he was able to derive some results that were later confirmed by the modern subatomic theory called quantum mechanics. In any case, this is the point where we introduce H, Planck's constant, which is discovered or created, defined by Max Planck in 1900. So we're deep in the subatomic world. And there was lots of activity in a small group of physicists working in the subatomic measurement and theory until 1925. And two students at the University of Leiden were able to resolve some mysteries related to spectra by postulating that not only does an electron orbit the nucleus of an atom, but that the electron itself inherently has angular momentum, now called spin. And when I talk to groups about this, I try to point out that there's nothing spinning. This is not, unfortunately, it's an easy analogy to make, and I will make it tonight, that the electron or the muon is a spinning object, like a top. That's really not the case. It's just an inherent property of these subatomic particles. So not only does this angular momentum exist and influence the spectra of atoms, but it also creates a magnetic feature for a charged particle. The idea, once again, an analogy with our something we use every day, the current in a wire can produces a magnetic field. So I'm going to show you the very simple equation that describes the magnetic moment of an electron. Here it is, abbreviated by the Greek letter mu. And this has the definitions of E and M here and here, the electron charge and its mass. G is a number that's going to be central to everything I say the rest of the evening. And S is the amount of spin associated with a particle. So this magnetic moment of the electron, if we put in Bohr's estimate, which turns out to be correct, that it's Planck's constant divided by 2 pi, and then divide that by 2, put that in for the spin, we have 2m, we have E, we do some arithmetic, and it turns out, it took a while to figure this out, a couple of years actually, after Uhlenbeck and Gauss-Schmidt's proposal. It took a couple of years to figure out that there is a factor here that in classical electricity and magnetism, this factor called G is equal to 1, but in quantum mechanics it's equal to 2. And so we do a little arithmetic and we get this as the magnetic moment of the electron. And the magnetic moment simply means this is the susceptibility of the magnetic moment to feel a force, the susceptibility of an electron in a magnetic field to feel the influence of the magnetic field. So the charge, Planck's constant over 2 pi, 2 times the mass. And this just reconfirms something I just said, that for classical work, when you design electric motors, for example, you can use the same kind of terminology with G equal to 1. In the world we're in tonight, G is equal to 2. This was discovered by Thomas. And Thomas's determination that G is equal to 2 predicts or predates something we're going to talk about next. But first, a little humor. In 1925, Niels Bohr, who was based in Copenhagen, was already, other than Einstein, the most famous scientist in the world. He had tremendous influence over the physics community. He had started his own physics school in Copenhagen, and I think by then he had won the Nobel Prize. In any case, Bohr left Copenhagen on his way to Leiden to a celebration of a old physicist's 75th birthday or something like that. And on the way, he had already left Copenhagen when Uhlenbeck and Gauss-Schmidt's paper came out announcing their idea that electrons inherently have spin. And everybody was all a Twitter about this. So when the train got to Hamburg, Germany, Wolfgang Pauli and Otto Stern met the train, and they found Bohr on the train, and they only had a few minutes, and they said, the two guys in Leiden think electrons have spin, whether they're in an orbit or not. And Bohr thought about it, and he said, that sounds very interesting, which his biographer says, a man who knew him, says that's how Bohr said a theory has to be wrong, to call it very interesting. So Pauli and Stern let him get on his way, and the next stop was in Leiden. And in Leiden, a number of famous physicists, including Paul Ehrenfest and Einstein, they were there for the celebration that Bohr was going to attend, and they met the train. And they said, what do you think about spin? And he said, I don't think it can be possible. And he explained, he gave him a technical reason having to do with what the electron sees when it orbits the nucleus, which has, of course, a proton, if you're thinking about a simple thing like hydrogen. And Einstein explained that Bohr was misunderstanding what's going on, and that relativity, Einstein's theory of relativity, says that what Bohr was concerned about is not a problem. So Bohr now is beginning to change his mind about whether spin of the electron is possible. After the event in Leiden, Bohr got back on the train and he's heading for Berlin, and in Göttingen, Heisenberg and Jordan, two famous physicists, met the train. And they said, what do you think of spin? And at this point, he said, I'm an advocate for it. Einstein has helped me understand my misunderstanding, and I'm an advocate. So on he goes to Berlin. And Wolfgang Pauli, who already met him in Hamburg to talk about this a few days earlier, went to Berlin specifically to find Bohr on the train again and says, what do you think about spin now? And Bohr had been thinking about this the whole time during the train travel, had already written equations and had a new idea of the whole concept, and became a vocal advocate for the idea, and returned to Copenhagen. So this is how science was done back in the day. You found the guy on the train and asked him what he thought. So now we're going to go back to the science. The magnetic properties of the electron and its partners, I'll show you who they are in a second. These properties, the magnetic properties, can be detected by putting these objects in magnetic fields. And electrons, which of course are in abundance, you can go to the store and buy piles of them. They are called leptons. They're in a family of these light subatomic particles I've already shown you in the standard model. And the electron has two heavier partners, the muon and the tau, as well as the neutrinos I pointed to. They are not part of today's story. Each of the leptons has the same spin, 1/2, but the muon and the tau are heavier than the electron. They have many of the same features except for mass. And as I've said before, the inherent spin in these particles imparts a magnetic property which allows you to tinker with them in a magnetic field. So once again, we have this somewhat misleading, but it's good enough analogy that the electron actually has a spinning component. In fact, what it has is angular momentum. Nothing is rotating in the electron. So now we come to Paul Dirac, 1928. So it's 3 years since the concept of spin has been introduced. Dirac, who later won the Nobel Prize for this elegant equation, produced the first integration of electromagnetism and relativity. And it's captured in this equation, which describes a relativistic electron. And this is extremely useful because it was the first time people understood how to write using the new formalism of quantum mechanics that emerged in the mid-1920s, how to describe the behavior of electrons that are moving at relativistic speeds. In so doing, in producing this equation, he kicked off what I will show you to be the most accurate theoretical model of any process in nature that has ever been developed. And it relates to something called quantum electrodynamics. That is, the way quantum particles interact with electromagnetic fields. In the process of producing this equation and in seeing what it implied, Dirac realized that there must be an antiparticle relative to the electron. That is, a particle with the same charge, the same spin, but not the same properties, in the sense that the electron is what we call matter, and its counterpart, called the positron, which plays a role in our story tonight, the positron must also exist. It's the same as the electron, but it's a virtual particle. And when the positron and the electron meet, they disappear and they produce a photon. They produce light. So this was a speculation interpreted from his relativistic electron equation, and the positron was found just 4 years later, which secured Paul Dirac the Nobel Prize. All this time, people were looking at the spectra of atoms and gradually improving the technology. So in the old days, if you looked at the spectra of, I think this is hydrogen, you would see 3 lines, energy levels, by energizing the electrons and looking at the separation of the energy levels. The new theory that emerged from Paul Dirac and Thomas, who provided the proper value for G, this actually explained what was observed as spectra became more accurately depicted, that there were little spaces here. There's what's called a doublet here that had not been seen. Well, it had been seen, but it was fuzzy. People didn't know what it meant. But the new theory that started emerging after Dirac predicted these splittings here and here. So people were already tuned into improving spectroscopy, and by the 1940s, new techniques had been developed, better than optical techniques, because all the earlier spectra were taken using optical or infrared methods. By the late 1940s, people moved to the microwave spectrum. And a lot of the technology that they used was derived from new industrial techniques related to radar, the development of radar and so forth. So there was a new window into subatomic physics by the late 40s, and people began looking at 2 things with very exquisite measurements. They discovered something called the Lamb shift, which I will describe in a second, and the magnetic moment of the electron got a lot of scrutiny. So we had technology for measurement and theory coming together to produce new insight into the subatomic world. So let's talk about the Lamb shift. This is the first big success for the offshoot of Paul Dirac's quantum electrodynamics, abbreviated here QED. So the Lamb shift, which I'll show you an example in a second, can be measured in the hydrogen atom by looking at electronic levels very precisely. And the energy levels are a little different than what Dirac predicted. He was close, but there's a subtle little difference that got people's interest. And this is in the period from 1948 through maybe 1951. And people who had been thinking about the subatomic world began to realize that vacuum particles, that is, virtual particles, spontaneously leaping into and disappearing from our universe, were interacting with the electron of a hydrogen atom and changing its energy levels. So this is the first evidence that virtual particles, which were, I'll show you in a second, were always allowed, in fact required by quantum mechanics. The first evidence that they have an influence on the way real matter behaves comes from the Lamb shift. And so using microwave spectra, and which gave very precise measurements, and a new mathematical technique called renormalization theory, Hans Bethe, who's pictured here, managed to show or derive the Lamb shift and explain why it should exist. This is the next big step in modern quantum electrodynamics. So Lamb won the Nobel Prize in 1955 for discovering the Lamb shift using a very precise experiment. Hans Bethe, who later won the Nobel Prize for explaining how energy is produced by the sun, he's the first to explain why the hydrogen spectrum is shifted in a very tiny amount. And here's the depiction. When Niels Bohr did his planetary model of hydrogen, which was, as I say, now is defunct, starting in about 1925, the better theory of wave mechanics came along. Bohr had made this prediction for the energy levels in certain parts of the energy spectrum of hydrogen. Dirac got these results. Quantum electrodynamics predicts this result. So this hyperfine splitting right here into these two distinct levels is the Lamb shift. And the key thing that Hans Bethe did to calculate this shift accurately was the renormalization. And here's the problem, and I'm going to show you this in a little more detail as we go along. Anytime you do computations in the subatomic world, you have to deal with the virtual particles that are interacting with the thing you're interested in. So if you're interested in an electron orbiting in a hydrogen atom, you must take into account the fact that the electron is in a bath of virtual particles popping into and disappearing from existence. These particles include everything: high energy, high mass particles. The law of the uncertainty principle not only allows but requires the presence of this foam of virtual particles. And so when you do calculations, it's very common that computing, say, an energy level of this energy level produces an infinity in the results, because you have to include the effect of an infinite number of virtual particles interacting with the thing of interest to you. And Hans Bethe dealt with the infinities by not calculating energy levels separately. He calculated these differences. And in the process, he became one of the pioneers in what's called renormalization theory. You find a way to do the arithmetic so that the infinities are suppressed. And this was the first big success for quantum electrodynamics. So here's a little more about renormalization. There's a group of people who were developing techniques for dealing with the infinite contributions of all the virtual particles interacting with the components of the problem you're working on. And remember, we're talking now strictly about electrons. We haven't gotten to the issue of muons that was in the press 3 weeks ago or so. So Casimir, Bethe, and others that I'll show you were very interested in how to manage these infinities. One technique they can use is to build the mathematics and then replace the terms that accumulate to infinity by experimental results. That is, you have a series of terms, an infinite series, and you terminate that series, and on the part that survives, you do with conventional math. The part that doesn't survive, that's leading to infinities, you replace by laboratory measurements. That's one way to deal with this. Other cases require manipulating and grouping the effect of the virtual particles, and in that case, some of the terms can cancel. Not every theory in the subatomic world is renormalizable, though. It happens that quantum electrodynamics is, which is a terrific gift from nature, because if managing a simple problem, like calculating how the electron should react to a magnetic field, if that was a non-renormalizable problem, it would have stymied efforts in the theoretical world and delayed progress. But luckily, QED is renormalizable, and here's a depiction, a graphical depiction of what goes on. Here's an electron on its merry way, the arrow illustrating time. But along the way, it can emit or interact with a virtual photon, this wiggly line. And what's more, that virtual photon can spawn virtual particles of every size and shape. And in the extreme case, we have a photon interacting with virtual electron and positron pairs. Remember, I said an electron symbolized by E minus, and its antiparticle E plus, the positron. Those two, when they meet, they produce a photon, this. And that photon can decompose into an electron and a positron, which can merge and produce a photon. So you have an infinite pile of these processes going on all the time. And as the author of this page points out, the bare charge of an electron is actually infinite. What keeps it from being infinite in the laboratory is when that charge is present, virtual particles around it that have charge are polarized by the presence of this real particle. The positive side is attracted because the charges, the negative and positive charges attract. So we end up, for a tiny fraction of a second, this electron in red is surrounded by virtual charged particles in a cloud. So that if you're outside this and you look at or try to compute the influence of this charge, you don't get an infinity, because this cloud of virtual particles shields that infinity away. It took years for people to develop this idea and really put it to work and understand how to do the computations related to vacuum. This is called vacuum polarization, and you need techniques of renormalization to make the math work. Here's another way to look at what's going on. This is the uncertainty principle in its technical form from Heisenberg. And what he showed in the 1920s is, or actually as early as maybe 1919, he was showing his colleagues this, and before he published, that if you investigate a small region of space and look for energetic particles, your uncertainty about how many energetic particles of different masses exist depends on how long you look. If you look for a very brief time, there must be energetic particles such that the product of the interval of observation and the range of energy levels that are present, that product of those must exceed this number, Planck's constant. And so these drawings done by John Wheeler are intended to depict what he called quantum foam, that this rule, the uncertainty principle, requires the presence of a surging foam of virtual particles that never stops. And so here are the words that I just said. Now, let's talk about the anomalous magnetic moment of the electron, which is the big achievement in the early 50s, building on the work done by Hans Bethe on the Lamb effect. People turned their attention to measurement of the magnetic moment of the electron. And I showed you earlier that it just takes some simple arithmetic using Dirac's equation to calculate what the magnetic moment should be. But the measurement, very exquisite measurements using microwave techniques, did not agree with Dirac's result. So this is called the anomalous magnetic moment. That is, there's something about the magnetic properties of electrons that is not predicted by the theory. The theory and the measurements did not match. So the issue focused on G. Remember, Dirac and others showed that G is 2 for for leptons, namely the electron and its family. But there's this term A, this is the anomaly term, and it's just a choice of those who invented this development to say that G, which would be 2 if Dirac were right, there's another term that has to be conjured with, and it's defined this way, that G is equal to 2 plus 2 times some little number, which we call A. And we're going to talk about A for the rest of my presentation. So the point is, it was shown that electrons do not have an A equal to 0. If A is 0, it means G is 2, and Dirac has described everything. But Dirac did not include the effect of virtual particles. So people realized right away, virtual particles interacting with an electron is going to change how the electron interacts with a magnetic field. So we should figure out, how do we compute A? So A, and measurement showed A is not 0 and G is not 2. So just rearranging a little algebra, we're going to concentrate on this. This is why this talk and all the press releases related to this topic are called G minus 2. It's all about, if G is 2, A is 0, but G is not 2. G is influenced by virtual particles getting into and interacting with electrons, whether they're in atoms or not. So we now know from exquisite experiments that G is equal to 2 plus this little bit. So that means, using this definition of A, that A is equal to 0.0011 such and such. So it's a tiny adjustment, but unless we can get this adjustment right, we don't truly understand how electrons are performing. So three people now come to the fore in our story. Schwinger, Feynman, Richard Feynman, who you probably have heard of, and Tamanaga from Japan. They built on the work of Hans Bethe and others, and Casimir, and they immediately are confronted in trying to explain the anomalous magnetic moment of the electron. They're confronted with renormalization challenges. They each chose a different path to attack this problem. Schwinger, in 1947, already had produced a result I'll show you in a second, where he realized that this issue of virtual particles was changing the results. And he came up with a first approximation, 1947, and it has to do with a number that's everywhere in quantum physics, this so-called fine structure constant, which is 1 over 137, and he found that divide that number by 2 pi, and you get a new result for G, which is close to what was measured in the exquisite experiments. They went on to continue this work and do 3 different approaches to renormalization and won the Nobel Prize in 1965. So here's Schwinger's first attempt to understand what G should be. It's equal to 2 times this little addition of 1 over 137 divided by 2 pi. And in fact, this is on his tombstone, alpha over 2 pi. These are the 3 guys who won the Nobel Prize. The interesting thing, I've seen a video of Schwinger and Feynman at a blackboard, and Schwinger is basically showing how he did his computation to go beyond this result and make it even more accurate. Feynman is standing there watching, and when Schwinger gets done, Feynman says, "I see what you did. I got the same result. I don't understand anything you showed me." So Feynman goes to the board and he shows what are called Feynman diagrams, which is a graphical computational technique. Schwinger watches politely and at the end says, "I see you got the same result and I have no idea what you just did." And separately, Tamanaga, who spent most of World War II hiding out in Japan, trying to not be killed, he had yet a third way to do it, which was independent of these two. And then we get Freeman Dyson. Who I met once, by the way. He was the tiniest man I've ever met. A very interesting character. And he turned out, he was the only one who could reconcile Schwinger's and Feynman's approaches. And eventually showed that those 2 techniques and Tamanaga's were equivalent. And unfortunately, the Nobel Prize is only awarded to groups as large as 3. So Dyson, who knew more than anyone else about what was happening, was not selected for the Nobel Prize. The other 3 were. So there's some text here if you want to read this. You can grab the charts and read about what his role was. But here's the success that Schwinger, Feynman, and Tamanaga eventually produced by maybe 1953. All the results were in. They extended Schwinger's result, this term right here, and they added more terms to that infinite pile of interactions with virtual particles that Schwinger only touched on in his work in 1947. And here's what they produced. This is the anomalous magnetic moment of the electron, and this is the theory. So starting here, we have 3, 6, 9, 12 decimal places of sensitivity for the predicted value. And if you go here to the most recent measurement, which is probably from 2015, 2016, we have 3, 6, 9, 12. In the 11th digit, there's a divergence between theory and measurement. And notice that the uncertainty is out here in the 15th through 17th digits. So what is now accepted is for the electron, the anomalous magnetic moment is known to about 1 part in a billion. To do this, you have to measure G in laboratory experiments to 1 part in a trillion, and that has been achieved. This, what I've highlighted here, is the most accurate prediction in the history of science. And it comes from including layers and layers of the influence of virtual particles interacting with the electron that you're staring at. There's Schwinger's original result. Now we're going to talk about the muon. The muon is the next bigger lepton after the electron. And by the way, this is from this, if you want to watch this in detail, this is the result of essentially a press conference where Aida showed results from the theory group looking at the anomalous magnetic moment of the muon. And so she gives a talk for about 20 minutes, and then there's about a 40-minute talk by the head of the experiment team. And this you have seen before. This is how we calculate the magnetic moment of the muon, which is the same as what you do for the electron, except the mass of the muon is roughly 200 times bigger. It has the same spin. And the question is, can we measure the G for the muon as accurately as we've been doing it for the electron for the last 65 years? And can we get this right? So here, once again, Dirac says G equals 2. And his presumption was, for all leptons, that the virtual photon that might be emitted or interact with the muon is described by an event that occurs at a geometric point. So his theory does not include virtual particles, whereas the real experience from the electron case shows us that, in fact, there's this region here, a surging foam of virtual particles that the muon joins, and then a virtual photon gets involved and the muon ends up coming out. But in this cloud, in this pink circle, lots of strange things are happening. So once again, we have G is equal to 2 plus 2a, and measurements have been made of the magnetic moment of the muon. And we have, once again, a standard model for subatomic particles that's very successful. It predicts all kinds of things like the masses and the debris products of the subatomic world. Goes beyond, far beyond what Dirac did in 1928, where he had this single point interaction, and the standard model includes all these virtual particles. So once again, we have the misleading but unavoidable analogy to a top, but we're going to emphasize here that the muon has the same charge and the same spin as the electron, 200 times more massive, but it has something else that makes it hard to deal with. The electrons are stable. Like I said, you can go to the grocery store and buy a bag of them, and when you get home, you still have that bag of electrons. Muons are not that way. They're produced in high energy activity like cosmic rays or in accelerators, and they are unstable, and they live 2 microseconds in a laboratory. If you just have one sitting on the table, its half-life is about 2 microseconds. Interestingly, though, the muon, when it decays, and this is the antiparticle of the muon pictured here, it decays through a strong interaction and some stuff, and you get 2 neutrinos, and you get a positron. And the positron is going to play a role in what I'm about to tell you. Remember, that was predicted by Dirac back in 1928, 29 or so. So here's a nice depiction of the particle zoo. I showed you on the first slide a flat version of this, but this is a nice way to look at it. What this shows us is there are three known families of particles. Let's start with the electromagnetic component, the electron. The electron interacts with things built out of up and down quarks, because out of up and down quarks you can build protons and neutrons. And those are the items that occupy the nucleus of all the atoms in the periodic table of elements. The electron makes that interaction, and when these things change, for example, neutrons decay into a proton, an electron, and an electron neutrino. So this group is considered to be a family. The muon, which is now the topic of our conversation, has a different community. It interacts with the charm and strange quarks and interacts with those most strongly. It's still a charged particle and it'll interact with electrons and stuff, but it has a familial relationship with different quarks and different neutrinos. And then the tau is the biggest and heaviest of the leptons. It's not part of our story, but it interacts with the top and bottom quarks and the tau neutrino. So this is the way people think about this. And the reason they build these charts like this is the results I'm going to show you in the next 10 minutes indicate there's something missing from this model of the subatomic world. And maybe there's a fourth family. So the positron is going to be important, and this statement in this heading that comes from the reference is incorrect. The electron and the muon have a relationship where this guy is 200 times more massive, but the statement here that the size corresponds to particle mass, that's not true. Anyway, let's go on. So here's a recap. If you put a lepton, like an electron or a muon, in a magnetic field, it looks like a top, and it nutates around the lines of magnetic force. While it's doing that, it's interacting with all kinds of complex things. These drawings are an attempt to show that there's a cloud of things blinking in and out of existence, interacting with, in this case, the muon. And we actually have measured the muon anomalous magnetic moment. Here it is. In an exquisite experiment done between 1997 and 2001 at Brookhaven National Lab, they measured the magnetic moment, and then they compared it with theory. And I'll show you this. So here's a depiction I just found today of, this is a box that is a 2.5 by 2.5 by 4 femtometer box. And this tries to depict the surging foam of virtual particles that exists in that little space. And they call this the quantum chromodynamic lava lamp. Okay, so let's look at what's interacting with the muon. Let me check the time real quick. Okay, I got about 10 minutes. The calculation of the expected anomalous magnetic moment of the muon is done the same way you do the electron problem, but it's more complicated because, remember, the muon interacts with heavier quarks, and that changes how you do the computation, because the muon can participate in nuclear processes. So there is a quantum electrodynamics effect that the muon undergoes, interacting with photons and virtual particles associated with the photons, but it also interacts with bosons, the pieces of neutrons and protons. So, and I will show you, so this is the computation for the anomalous magnetic moment of the muon, and it has three parts. It has the same quantum electrodynamics issues of virtual photons interacting with the charge of the muon, keeping in mind the muon is more massive. Then we have these heavy particle interactions for the W particle, the Higgs boson, and the Z boson that electrons are not influenced by. And finally, there's this neutron-proton interaction, which is greatly suppressed in electrons. So the computation produces a different number for the muon than you get for the electron. The measurements give you this, and the deviation is right here. So we don't have 11 decimal places, and people are concerned about why is there an 18 there and a 20 there. So this is just a little more detail. The muon has quantum electrodynamics. It has influence from weak forces. That's what the Z boson reflects. And then it has vacuum polarization effects and something called light by light, where a virtual photon, turns into a cloud of physical particles and returns to being a photon. So that's called light by light. And each of these contributes, as I showed you on the prior page, to the expected value of the anomalous magnetic moment of the muon. So here's what they showed in Brookhaven National Lab on Long Island, 1997 to 2001, and they got this value right here. We don't have to worry about the units. They got this value. Keep in mind that you're working with particles that only last a short time. So if you get them to relativistic velocities, you can look at them for a longer time, but it's still a different kind of experiment than doing electron quantum electrodynamics. And here's how the theory has evolved over the last 15 years. They've done more and more work trying to add more terms in the computation, and the uncertainty, this blue wedge, has gotten smaller, but there's still a distinct difference measured by the statistical measure, a distinct difference between measurement at Brookhaven and predictions done by the theory group. So the idea some years ago was, let's redo the experiment done 20 years ago by bringing the ring where the interactions are observed. Let's bring it to Fermilab near Chicago, where they have a big accelerator and they can produce large quantities of muons and run them to higher velocities so they're more stable, because of relativistic effects at higher velocities, the apparent lifetime of the muon is increased. And their goal was to reduce the error or the uncertainties observed at Brookhaven by a factor of 4. So they were going to do experiments with 20 times the number of muons and drive down the errors. Now this ring, they didn't want to build another ring. You can get a sense of the size. These are things the size of a refrigerator. They didn't want to build another ring. They just wanted to take this ring to a better accelerator and equip it with modern electronics. And you can't take this thing apart. So this is a artist rendition of the Fermilab near Chicago. They built 3 buildings for doing this work. It took a long time to do that. And they moved the ring from Brookhaven by barge to the vicinity of Chicago. Here it is. Well, there's a tractor of a tractor trailer. This, they packaged it very carefully because they don't want to injure it. Put it on the barge, traveled 3,200 miles. Here it is going past St. Louis and so forth. There's a sense of how big the thing is. They had to pick the route carefully and, remove the mailboxes as they went down the road, pick the right tunnels and bridges so they didn't have to take the bridges apart. And here it is when it finally was settled in at Fermilab. And here's some people. It gives you a sense of scale. But it's now attached to a big accelerator that produces an abundance of muons, and we can redo the experiment. And the way the experiment works is they put clusters of muons into this ring, into a storage ring, and it turns out that when the muons are propagating around here, they decay. As I mentioned, they decay, and one of the decay products is positrons. And those positrons are easy to find because they're charged particles. And if G is exactly 2, the ring of muons going around and the resultant direction of the decay particles, the positrons, are well known. You can measure that very accurately. But if G is not 2, you get a different result. There's an angle that develops as the particles decay. So here's what happened. We want to confirm that the Brookhaven experiment was done correctly, but with better measurement, and that is the case. Here's the Brookhaven measurement done 20 years ago. Here's the Fermilab measurement. These two are in this purple bar. They are very close together. Whoops. And they're way far from the standard model. So Aida, who I showed you earlier, and her team are now trying to up their game theoretically, but that's a big gap to cover. And as I said before, people are now speculating that we have to introduce new particles to understand why there's such a big difference between a very carefully done experiment at Fermilab and the standard model of subatomic particles. So that's my last technical slide. I want to recommend this book if you're interested in this topic. It's by Feynman, dates back, I think, 1985. It's a wonderful small book about quantum electrodynamics and all these the issues related to virtual particles and a lot of other subatomic issues. And I recommend this for you or young people in your family who are interested in this topic. So I believe, yes, that's my last slide. So I'd be happy to entertain questions.
Thank you, sir.
Ed, I just happened to be pick up one of my science journals that I'm way behind on, and they were talking about in the experimental stage of this, they were doing essentially a double-blind study. So there's something about frequency of clocks, and they were hiding the frequency, and only 2 people in the country where that was. I didn't really understand it, but it sounded like, cloak and dagger. It was really interesting.
Well, let me clarify for you. That's exactly right. So let's go back to the first drawing. I have a reference here, right? I think, right? Yes. If you go to this link I talked about, it's essentially a press conference. Aida and the theory team did not know until the very end of the experiment what was measured in the lab. And during the presentation, the real-time presentation that was recorded, she, for the first time, sees the result. And the result is captured in the frequency. Let's see if I have it here. Yes, right here. When they do this experiment with the clusters, or what they call bunches, the decay rate occurs at a frequency expressed here. It's the frequency associated with the anomalous magnetic moment. If you do the arithmetic, you find that the frequency depends on the size of the anomalous magnetic moment of the muon and the magnetic field that is produced in the ring. This magnetic field is measured with exquisite detail. They have many, many calibrating techniques. So if you measure the frequency, you automatically know the value of the anomalous magnetic moment. And that's what was revealed to Aida and the theory team, is the frequency. And they knew what frequency the theory predicts, and they had to wait until the end of the presentation to find out what frequency the measurement produced. And the result was they don't agree. So that's what they're talking about when they say the frequency double blind and so forth.
That's pretty cool.
Okay, other questions?
Fascinating talk. And really, as I was listening to your description of vacuum, couldn't help but imagine that perhaps there's a way to think about a temperature of vacuum. I mean, I know you don't ascribe temperature, but maybe the density of the virtual particles appearing and disappearing, or the rate at which they appear and disappear, could be related to a term like the temperature. I know it's not temperature, but something like that.
Yes, and so there actually is such a thing. and it was introduced by Casimir in the late 40s. Now, we don't have to go time to go into the details, but Casimir was very interested in virtual particles. He made a prediction. Actually, maybe I can pull it up if people will indulge me. I'm going to talk while I look for something. Casimir made a prediction of the influence of virtual particles and how that should be a measurable thing. And it took 50 years to do the experiment, and he was proved right. At the time, the major thinkers in physics thought he was nuts that you could measure the vacuum energy. Yeah, let's see if I can pull this up. Now you guys are still seeing my screen, I hope.
Yeah.
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 Okay. So I have this presentation. I could give it in 15 minutes, Bruce, if you want to see, if you want people to see it. And let me just describe it very quickly. Casimir said, virtual particles come in all sizes and shapes, and each one of them has what we call in quantum mechanics a wavelength, or the size of the wave function. So let's do the experiment. We take two plates and put them extremely close together. And in the process of doing that, we prevent virtual particles with a large spread in their wave function. Those particles will not fit between the plates. So outside the plates, and this is all done in a vacuum, outside the plates, all particles are allowed, but inside, only the plates of higher energy or shorter wavelength are allowed. The result is you have a differential pressure on the plates. You have higher pressure on the outside, less in between. And Casimir did a calculation, which I will skim over briefly, and said, I know how to calculate the force that should be exhibited on these plates. And as I said, people thought he was nuts. So this is the theory. And here's the result. In 1985 or 87, people finally did this experiment. This is the plate separation in nanometers. Remember, a wavelength of light is 400 nanometers. So green light is right there. These plates are exquisitely close together. And here's the force predicted by Casimir. And if you look here, the theory is the dark line, and the squares are measurements. There's a little adjustment required because charge accumulates on the plates. So they had to do, there's a little adjustment. But even if you forget that and follow the dotted line, Casimir predicted correctly that there is a force. It's not a temperature per se, but you can measure the force between plates due to the presence of virtual particles of all sizes here and exclude some of them here. I hope I addressed your question.
Thank you. I have to leave.
Okay, thanks for attending.
So,
Thank you
Ed, I have
so
another
much.
question. As a lifelong chemist, my image of the rotating electron is how I do chemistry. And now you're telling me they don't rotate.
Yeah, there's
How can I put that imagery in I mean, it served me well, but can I put that imagery correct?
Yeah, I think you have permission to do what everyone else does and visualize a little rotating thing,
Yeah.
but there's nothing rotating. It's just the particle is born with angular momentum, and it can't lose that angular momentum. That's the key point.
But if it's not,
And another feature is there's only the electron can have a half a spin up or half a spin down, depending on, it can't have any other value.
right, but we were always taught that it was spinning up or it was spinning down.
I can't quite hear the question.
No, we were always taught that it was spinning looking up or spinning looking down, and that's the whole thing about electrons, spin resonance and
Right, exactly.
that we did all the time.
And it doesn't matter if you change the orientation of your magnet in your laboratory, you can define up and down any way you want, and the electron will cooperate. It will only have up and down in whatever experiment you do. It's mysterious. Yeah, there's another pair of young scientists, Stern and Gerlach, who were baffled by this when they did experiments on a beam of electrons. No matter how I orient the magnets, I get the same results. It's
How they do it without spinning? Well, I guess-
And
and that's-
it's used for some tricks in quantum computing.
oh yeah,
Yes, yes. You know, there's a couple of things that come out of this. One is that now they feel that there's other things out there that we have not yet identified that is causing this gap. And
Right.
they're saying that the standard model may be proven to be incomplete. As a result, there's more to be found, which I find fascinating. And I'm also fascinated by the fact that the Higgs boson, which is our mass, decays. And one of the things it decays into is a muon. So, you know, the muon has a lot of mass because it's bigger, and it is part of what the Higgs boson gives us when it decays. And I'd love to know more about that too.
yeah. So that's what I was saying, Judy. That the implication of the experiment and the gap between experiment and theory suggests that there may be a fourth family here,
Right.
and there's a lot of speculation about dark matter in the universe. Is that possibly related? If you watch the press conference I referred to, you'll see the head of the experiment team talking about that and
Right.
what it
Kept
could
saying
imply.
that.
Yeah,
We
you
saw that press conference, so it was fascinating. The whole process they went to, watching in real time, practically them move that entire ring through tunnels and over bridges. It was amazing, but fascinating to see the look on everyone's faces when the results were revealed. The team was screaming and cheering, and
yeah.
it's very, yeah. I'm gonna go back and watch it again. Thanks for the link.
All right,
Okay.
I have a perhaps naive question. What do you physically mean by angular momentum if you don't have a spin or something revolving, or
Yeah. Well,
what
this
do you
is
mean by angular momentum?
Thank you, that's what I was saying.
well. Here's the thing: you are measuring spin, which everybody associates with angular momentum, and there is, as Bohr showed, you can calculate from primitive ideas of the atom. You can calculate the relationship between spin, angular momentum, and magnetic moment. But the fact that the electron is born with one of two values of spin, no other value can exist. It can't give away its angular momentum like a merry-go-round. If you grab it and slow it down, you can have any value of angular momentum you want. Electrons don't behave that way. They are, it's akin to this issue of our electrons, particles are waves. Depends on the experiment you do. If you're looking for waves, you can find the electron will cooperate and behave like a wave. If you design a different experiment and insist that it behave like a particle, it can do that too. And it has no, cognitive capability, but somehow the electron knows what to do. If you put, and some of you will recognize what I'm about to say, if you build a double slit experiment, electrons know there are certain places they are not allowed to go. How that's possible, no one knows, but it's a property of the mysterious subatomic world.
Well, actually, may I say something about that?
Sure.
It goes even further, and this is the part that always blows my mind, that I can do that experiment. I mean, you know this, and I think everyone else does too, but it still blows our minds, I think, that I can send electrons to do that experiment and send them out at such a low rate that there's only one electron at a time.
Right.
impingent on the slits, and I still get the pattern.
Yep.
So in effect, the electron is interfering with itself, and that always blows my mind.
Yep. And yes, exactly right.
It has to decide which way to
Yes,
go.
and you can actually do that. High school students here at Gateland Kaplan in Portland have been doing that with photons, where they send one photon at a time for double slits, close it, and then open it after the photon has gone through. And it knows when it's detected on the other side. High school
Yeah.
students can now do that.
Yeah, this is called the delayed choice experiment,
Right.
invented by John Wheeler. It looks a lot like a baseball diamond. Once again, I could do 15 minutes on that, Bruce, if you want.
Please do.
It's a mysterious thing, and in fact, people are talking about doing that experiment with light from stars, where the light was born billions of years ago, has no idea what it's going to encounter on its travels, and you can demonstrate with such an experiment that it doesn't matter. The light comes into the experiment not knowing what it's going to be exposed to, and if you design the system for particles, the light behaves like individual photons. If you design it to detect waves, you can do that too. Nobody can explain this. It's just.
Have you ever thought what must have been like in about 1900, early 1900s, to deal with this new world of uncertainty?
Right. And an additional layer under that was relativity was everywhere.
Yeah.
So if you were interested in the subatomic world, you couldn't produce a theory that people would take seriously unless it also was compatible with relativity.
Mm-hmm.
The complexity, that's why it took almost 100 years to really get to where we are now, and many people are unsatisfied with where we are now. But the problem is that quantum mechanics works, and you can design electronics and lasers and all the other stuff we rely on in our modern society. And nobody at this point, the advice young quantum mechanics are getting is shut up and compute. That is, if you want to work in the semiconductor industry, bring the tools necessary to compute results, and don't worry about why we don't understand why the equations work.
Yeah, as my friend Brian Greene says, we've been trying to unprove quantum mechanics for 25 years and have been totally unsuccessful.
Right. There's no refutation. It works. There's no doubt about that. But we know there's something big missing. In fact, Sean Carroll has a recent book called Something Deeply Hidden about this topic, where he tries to make sense of why it works and will we ever figure out what's underneath what we currently know.
Well, there's another weirdness too that always blows my mind.
That
The Bohr atom is wrong, of course, as we know, but you can still calculate with it. I mean, it's just.
Exactly.
Yeah, go ahead, Ed.
You can calculate the Rydberg constant, which it exactly predicts the hydrogen spectrum.
Yeah.
And from a theory that Bohr invented that looks like a little solar system, and we know it's wrong, but you get the right answer. How is that possible?
it's a little like, what does it mean for a particle to have a spin? When we know it has no magnitude, what happened? Doesn't rotate, means nothing. What we do, I think, is decide the particle follows the quantum mechanics of angular momentum. It obeys those laws. That's what we know about it. And that's why we say a particle has a spin.
Yeah.
Right.
So you're saying you really can't put that in your mind. You can't.
It's kind of disappointing.
You can't envision it as a spin up and down.
All right. Additional comments or questions, or are we done for tonight?
Thank you, Ed, for that very nice talk.
Thank
Took
you,
me
Neil.
back to my grad school days.
Yeah, thank you very much. I'm
Okay.
looking
Ed.
forward to the 15-minute night now.
Yeah,
We got, we have, we're gonna have some fun. And so anyway, Ed, that was, as usual, very, very instructive. I love the history. It just really, really fun. So
Great.
everybody enjoy the evening. It's 80 degrees here in Portland, so it's pretty nice. Hope it's nice where you are.
it's 56 on Long Island.
Yeah,
Oh, well.
it's been raining. It's been
It's
raining.
it,
Oh, well,
40s in Massachusetts.
okay. I won't rub it in.
What is that, 40?
But I'm rubbing on some suntan lotion right now, so see you guys.
Hey,
Thanks.
thanks, everybody.
Thank you so
Thanks.
much. I really
Thanks.
enjoyed it.
Good.
Thank you very much.
Thanks, Ed.